You know, when you talk about control mechanism, you have to sense something, right? You know, normally if you want to control the voltage, you have to sense the voltage. Some researchers, they develop algorithm to use some other variables that are being sensed, and they call it sensorless, not entirely sensor without sensors, right? You need to have some type of sensors. For example, in a permanent magnet synchronous machine, normally you have two phases, which is controlled by an inverter. You have two phases that are being energized. So the third phase is open. Well, that doesn't mean that you cannot induce a voltage. So if you sense the voltage on the third phase, basically it gives you an idea where the back EMF for that synchronous motor is. And so they use that sense voltage to know the rotor position. Well, they are going to call it sensorless. Well, what it means is that they don't have a shaft encoder that measures the speed of the motor. But you do have sensing of the voltage. A lot of time, you know, they call it sensorless, but for example, you need to measure current, right? What do you measure current? Because you have to establish your electric protection, right? What did the recloser do? What did the circuit breaker do? They measure the feeder current to determine whether you are in a fault condition or not. And then when they detect a fault, a trip signal is being sent. So when we talk about control mechanism for switch capacitors, basically we will see just now that there are a few, you know, not many. But voltage, right? You have a voltage regulation, right? And you run the first case without shunt capacitors in today's homework. And then you wanted to improve the the power factor at the substation, right? And then you put shunt capacitors. Well, you know that you don't have just one big switch capacitors. In today's homework, you run two cases, minimum load and maximum load. But in real life, right, you're not going to have one capacitor bank. You're going to have several, right? That's what you're going to have. You're going to have several capacitor banks. And so how do you turn them on? Well, in this particular case, it's time. Whenever the time is 10 a.m., the capacitor comes on. Whenever it's 10 p.m., the capacitor goes off. So what you need is a timer. And you need to have a clock, right? And so how you have to figure out that that clock works, right? It's not one that you have to wind up, right? So, you know, today you have digital communication and things like that. So obviously you can with smart grid, right? Today, you got a lot of communication systems, and so probably you need to somehow connect to this. And then the other is voltage. You just run an PSpice, if you use PSpice, and you saw that the voltage dropped. So you measure the voltage. And if the voltage drops below 95%, what do? You bring switch capacitors. Now, do you bring all of them? No, right? You bring one bank, the voltage is still below 95%, you bring the other bank. So all that is part of the design, right? So what you did in today's homework was a very simple exercise. You consider two operating conditions. How many operating conditions do you have here? Many, right? And if you want to consider the discrete ones, you have, the other day we saw 11 or 9. But in reality, that's a continuous function, right? So obviously the design of the system, right? But now, what do you know that we learned the other day on the last class? What's wrong between that figure, for example, and the other figure that we saw in the textbook? Right, if you look at this figure, right, what it says? That you're not going to have more than 2 to 3 banks. If you go back to figure 16, how many banks do you have? Right? You have quite a few, right? Well, it's not that simple, right? What it said is probably it's not feasible, right, to have more than 2, 3 banks at full load. This is your feeder, right, the same as you did today. And here you have that they put, here they have one that is 300 kVR F, right? It's a fixed capacitor that I put there, and it's before the voltage regulator. Why? Because if you put it on the other side, every time that this gives you a step on the voltage, you are going to get some inrush current, right? The VDT is equal to I divided by C. And now here, right, is 600 TH and T. Basically, the control operates on time, but they have also a temperature override. Because now it operates on time and temperature override, because what are the loads that you're going to expect here? You know, this is a rural feeder, houses, so they're going to have air conditioners. So most of the load is going to be inductive in nature. And so this is basically what they do, and they don't provide any, I don't know if half is on time, half is on, I think it's time and temperature override, but I don't have any other detail than what is written there. But there you see, here there are 1, 2, and we don't have anything, right? I don't see any. And look at that. There are no capacitors. Oh no, here there is one. Right, here is another one. There. Seems to be 100 kVR. Far away from this, so basically there is no step increase. And so basically here is time switch control, that's your T, and this is voltage switch, right? And that you have done that, and you see that when you have too much current, which is a lagging power factor, what's happening? The voltage drops. And when it drops below 95% or certain, you know, so here is sensing.